And all right, I believe we are live. Let's make sure here. Hello, everybody, and welcome to the Seattle RISC-V meetup with our special guest, Andrew Bunny Wang. I'll do a brief note here about the RISC-V Foundation, and we'll move on to the talk. If any of you have any questions, there should be a Q&A panel available for you to ask anything. What we'll do is try and address the questions at the end, give Andrew time to talk and get to the various topics that he wants to hit, and then we'll open it up for getting those questions that you have proposed answered. I see we're at about 27 participants, so there's more people than in the meetup group, which is great. I appreciate everybody that's showing up here. I believe we have some people even from the Tokyo group, so Hajime Mashite, I'm glad you could make it, and looking forward to getting this going. So let me just share a brief screen here. And the RISC-V Foundation has recently established a community page. Let's see if I can get the screenshot. And again, pardon for the roughness here, folks. Don't beat me up too much about it. So there are at community.risc5.org, you have the opportunity to sign into the foundation page and then note on that single page which communities you'd like to belong to. The foundation would like to have people transition from the various kind of random meetup pages to a singular place where everybody can get information and have a kind of a single point of contact and quickly disseminate information to all of the interested members. So when you get a chance, please make a little bit of time to go and join up on the community page for the RISC-V Foundation.org site. And there should be a group local to wherever you're at if you are a member of one of the meetups already, San Francisco, Seattle, for instance, here. So feel free to go there and tag yourself as belonging to that group, and you'll see the announcements for the upcoming meetups on there. And it should be a little bit quicker than, for instance, the meetup page getting information from the rest of the org. So, and with that, let's get off of that and go back to me. Okay, so my guest here, of course, as mentioned, is Bunny. As hopefully many of you know, he's an extremely prolific hardware hacker, author, just all around very inquisitive person, and from what I've seen so far, a really awesome personality. So if you have not picked these up, please check out his books. There's also another one which I have on ebook, but just Google the name. These are some of the best write-ups that I have personally read, just digging into the guts of how to reverse engineer something and kind of the curiosity that goes along with it, and the what I had referred to Andrew before, saying that the humanism of some of the way things go into your product, how your product gets designed. Sometimes people are designing a piece of technology that they'll never even use for the end technology, but they have such an intimate knowledge of a very small piece of that technology that is critical to having it working. So please check out the books. And without further ado, let's see, Andrew, you should be able to take control and
okay. Give it a try.
Yeah.
Thanks.
All right.
Thanks for the awesome intro. And thanks for the plug on the books. That's very kind of you. Let me see if I can get the screen share going first. Cool. I think I at least have that there. And let me see if I can get this into full page, full screen mode. Okay. Good. So I believe that there's also a video on the side as well that people will see, I think.
Yes.
And then okay, good. So you can also see me. I just asked just in case, like I want to hold something up to the screen or something, people can go ahead and see it. Right. So my understanding is that normally the meetup is a smaller format that's a little bit more intimate, and so I'd like to try and keep with that format the best we can in these virtual times. And so I'm going to go through sort of a deck that I have about Precursor, which is sort of my latest effort to try and create evidence-based trust in computing. But I'd like to sort of invite people to sort of put questions in the Q&A area. And if there's something in particular, if they feel like they want to ask something, go ahead and put it in the chat, and I'll try my best to sort of manage and answer questions on the fly. So this deck here, I'm going to spend about the first half of it trying to get everyone on the same page as to what it means for evidence-based trust and sort of the significance of it. The last half will get into the specifics about Precursor itself. So people who have seen this in my previous talks, the first half, you may have seen quite a bit of the material before, but I'll try to go quickly. Okay, so let's start with the question of, like, do you trust your computer? Why or why not, right? There's various reasons that people may have to trust their computers at various degrees. But overall, there's a general bias that people think that things are more open, particularly in software. And is it because we actually read the source of the Linux kernel, every single line of it, or that we compile it before we install it? I mean, the answer is absolutely no. We don't have the time of the day to go through that amount of complexity. But the key point is that software actually has evidence-based tools to transfer trust, things like hashing, public keys, and Merkle trees. Just as a reminder, hashing is a way to go ahead and take a huge pile of bits and reduce it to a short sequence of symbols, so we can quickly see if there's even a single bit change in a big file. And signing is a way to take that sequence of symbols, that shorthand for the file, and sign it in a way that any attempt to modify the file or the hash itself can go ahead and will be unsuccessful, right? So with a combination of hashing and signing, we're able to do things like transfer trust from a very remote location all the way to the point of use for the user. So in the case of people who are trying to deploy software over a large scale, you can have developers who are very far away from the end users, who are sort of represented here in the lower left of the diagram, committing code to Git, and itself has a kind of a cryptographic Merkle tree to go ahead and trace the history of changes. And they go ahead and throw it into a remote server. The server itself, the build server, needs to be trusted. But then at the point at which the binary comes out, a trusted user can go ahead and sign it, and you can transmit it through a completely untrusted network, put it on your disk, store it there. And then as long as you're sort of checking that signature just before it gets to the point of running it, you can go ahead and transfer the trust from the developers to the end user, right? And then you can also have auditors who can check the signature in the middle. And if the crypto hashes all line up and the signatures all line up, then you're okay. Now the question is in hardware, is there a sort of equivalent analogy? And the problem is that in hardware, we'll find is that it's basically a time of check to time of use problem all the way down the supply chain itself. So thinking about the situation in hardware, let's start with sort of you. And there's the problem of evil maids, which is like someone breaking into your house and putting an implant into your machine or whatnot. Let's not talk about that right now. Let's talk about more common scenarios of, say, you have a courier and a distributor, right? And on the way, someone goes ahead and intercepts the devices and puts implants on the inside. This is not a fiction thing. Actually, when Snowden put out his documents, there's like direct evidence that this is happening to devices, at least by one government. And then perhaps also more concerningly, there's the issue of like other customers with today's sort of online distribution methodology, where we go ahead and order things from Amazon and whatnot. Anyone can go ahead and order a product from Amazon, say a hard drive, take it out of its box, go ahead and install firmware on the inside of it, and put it back right into the supply chain by doing a return on the hard drive itself. So you don't even have to be, have a sophisticated operation where you intercept packages to go ahead and do things. You just have to have someone in the geographic region of the target you want, and then just sort of injecting things into the supply chain. There's ways to go ahead and tamper with, the tamper evidence stickers. Some suggestions is, using hot air to remove it. If you know the right people, you can just print your own tamper evidence stickers. They're actually not hard to go ahead and make anew. And plus, a lot of people don't even know what they look like at the end of the day. As long as they look pretty official, people are pretty much willing to accept them. And then, okay, so if we zoom out a bit from like the local issues of sort of distributors and customer returns, you have things like customs officers, you have factories that go ahead and build your stuff. If you go all the way back through the supply chain, all the way to sort of like the, PCB houses, the chip design houses, the IC fabs, the gray markets that are used to sort of, help businesses operate efficiently in the construction of components industry. It's a huge attack surface where anything can happen all the way back, to the chip design phase, right? And the question is, can open source save us? If we go ahead and, I've added to the diagram some developers on the left committing some code to GitHub, right? Does making everything fully open source actually help us? The problem is actually, it does help us somewhat, right? But the problem is that the place of check is too far from the place of use. So you go ahead and have your CI checks in the cloud, you have some open PCB designs, you have an open PDK, some open massets, whatever it is. There's that whole region in the middle where things can go ahead and can happen. I hear a lot of people talking about like, oh, let's have trusted factories, let's have some things on it, in our domestic soil. Let's go ahead and start onshoring stuff. It's only a marginal improvement, right? Because the thing is, you still, from the factories, you still have couriers, you still have returns, you still have things going into the factories that can be contaminated. So, it's only a marginal improvement. So at the end of the day, the big problem is that you just can't hash hardware. There's no hash function for hardware, no convenient, easy one-way, non-destructive method to go ahead and confirm that hardware is not tampered with. So as people, who may have read some of my books will have noted, I've always said there's always a bigger microscope. You can't hide secrets in hardware. This is true. There are really amazing microscopes that are non-destructive. They can go and image ICs in really high resolution and in a way that doesn't actually destroy it, or so the claim is, right? The problem with the methods of the ones that they can do this in modern ICs is that they need literally a building-sized microscope. The tychographic X-ray imaging that I had sort of referenced in the previous slide, that's a picture of the facility that's required to do it, and that donut-shaped building in the foreground is the light source. That's the equivalent of the light bulb for the microscope that can do that. So you're not going to really want one next to your house or in your lab. The second problem is that verify just one chip. So people say, okay, let's go ahead and pull one chip out. Let's take this, x86 chip I got, and I'm going to send it to the SLS and go ahead and get imaged. It only verifies that specific chip, right? It doesn't specify the copy of the chip that's on your desk, right? And that's literally the exact definition of a time of check to time of use problem, right? You wouldn't random sample the signature checks on your downloaded software. You want to check the signature on the software you plan to run yourself. So even if you could image a chip using such a fancy facility, it doesn't actually move the bar as to what hardware you're using. So the big question is, can we even do evidence-based trust in our computers? Is that a possibility given sort of the potential threat of these implants? I'm not saying that they're hugely pervasive, but they certainly seem to be evidence that they can't exist, and there is documented evidence of people putting efforts into this, right? So I've sort of gone through these several sorts of iterations on this and sort of tried to distill this into sort of a set of 3 principles. Complexity is the enemy of verification if you want to go ahead and engage in evidence-based trust. So you also want to verify the entire system and not just individual subcomponents, and you also want to help empower end users to verify and seal the hardware. And I'm going to try to very briefly touch on all these 3. Some people may have seen this part of the deck already, but I think there's also people in this chat who are seeing this for the first time. So the first problem is that when I say that complexity is the enemy of verification, the problem is that absent robust hashing function, verification literally falls back to an atom by atom exercise, right? So if I want to go ahead and take a modern smartphone and just confirm that it has all the parts it claims it's supposed to have, first of all, it's probably destructive because you had to break a bunch of glue seals. And second of all, like there's a lot of parts inside a modern phone to go ahead and verify. And it means there's a lot of places to hide things depending upon what your attack vector and your concern is. So we can go ahead towards very simple things that are very easy to verify. So this is the Monster 6502. It's one of my favorite projects out there. But a guy went and built a discrete transistor-based 6502. Like actually, you can see the transistors with your own two eyes. This is sort of like the other extreme of simplicity and verification. It's really easy to verify. You just look at it. The problem is that runs at 50 kilohertz, right? So there's not a lot. You're not going to be doing curve 25519, at least not anytime soon, on something that runs this slow. Now, you could build a processor in the middle ground that's sort of a visually inspectable process. Something easily inspectable is around 500 nanometers, like blue light's 380 nanometers large, and so even a kind of a commonly accessible microscope can inspect it. The problem is back at 500 nanometers, maybe 100 megahertz was the fastest clock rate we had. You're also going to have a pretty high power consumption because of the large geometry and the large voltages required, and you're not going to have a lot of RAM on the device itself. So even at the chip level, even at that level of integration, it's a little bit prohibitive in terms of trying to do something computationally useful. So it turns into sort of a trade-off at the end of the day, sort of the ease of verification versus features and use. Like on the left-hand side, I have a picture of AirPods. On the right-hand side, I have a headset. The two of them are basically functionally identical. They put sound in your ear, you talk through them, right? The one on the left has like 7 orders of magnitude more transistors than the one on the right. The one on the right has a single transistor, which is the FET that's used to amplify the microphone. You can take it apart, look at it probably, and you can use Maxwell's equations to go ahead and infer what's going on with the ear, because it's just a magnet and some coils. On the left-hand side, who knows what's going on? There's probably more code in that thing than I've ever written in my life, right? And it could possibly review. Even if you gave it all to me, I wouldn't be able to know what's going on inside of it, right? And the main difference between the two is one of them has a cord and the other one doesn't. I mean, the main difference, obviously, is some size and appearance differences. And so, but if you cared about evidence-based trust, you're going to have to make sort of the sacrifice of that complexity so you can get to something that can be verifiable, right? So we can't have our cake and eat it too, I think, when it comes to evidence-based trust, because we don't have hashing functions in hardware. So a second point I'm just going to briefly make is I think you need to verify entire systems and not just subcomponents. And so this sort of points to the whole sort of input and output problem, I like to say. So we already have security enclaves inside of our phones. This is a kind of a very cartoony diagram of a phone. You have an enclave, a CPU, a display, and a keyboard. Even if you go ahead and bury your keys in the inside of the security enclave and you trust that entirely, the problem is that you still have to get your messages to and from that enclave, right? And so if you've ever used an Android phone and you want to install a new IME, there'll be this little thing that pops up that you probably just click OK to. It says, this input method can go ahead and collect all the text you type, including personal data and password. And you're just like, OK, right? So you can put all of your secrets inside this security enclave, but then you just said, I'm going to trust all my passwords and all my text to this, completely untrusted random program to go ahead and help me type emojis faster or do AR on my face or whatever it is, right? Like, it's like, it doesn't really help to actually have that secure element for a lot of practical purposes for the things that you care about keeping private. It may help some vendors lock the device down and make it harder for you to do other things that you might want to do with it, but it doesn't necessarily move the ball forward on keeping your text messages secure. And so that's the reason why I say we have to do whole systems. And finally, I think it's important to empower systems to verify and seal the hardware themselves, as opposed to using a third-party service. So when I say verification, it should happen at multiple levels, at the board level, at the chip level, at sort of the design level, right? So facilitating all these types of verification, I think, is important, even if not every user can do it themselves. Other users being able to do it, I think, helps create a general threat of presence against people who are trying to do implants. And this, and particularly a lot of people who have worked with the RISC-V and other SOCs and stuff will be familiar with the problem that even, for example, burning eFuses onto devices oftentimes requires like a third-party piece of software. So you go ahead and you get like this wonderful open source tool chain, you build all these sorts of things, you generate your keys, and you say, okay, now I've got to burn the keys onto the eFuse all of a sudden using a third-party JTAG box with a closed source piece of eFuse burning software to go ahead and take your secret keys and put them into your device. You can't look into any of this. Is like a really common problem. And it's because a lot of vendors view eFuses as secret sauce. How do they work? What are the protection coding you have to have? Because eFuses aren't reliable. A lot of vendors don't want to admit that they actually have bit errors inside the eFuse themselves. And so they hide that underneath an abstraction layer. And so there's legitimate reasons why these guys think, legitimate, I guess, why these guys think they shouldn't be able to share their algorithms with you. But at the end of the day, there's even this sort of weird problem that after we've stripped back all the layers of closedness, when it gets to burning your keys, the fuse boxes themselves tend to be very proprietary. I also think the sealing maybe should be physical as well, depending on your threat model. If you care about evil made attacks, then going ahead and being able to sort of identify the key components and put a shield over them and seal them could be a helpful thing as well. So this brings us to Precursor, which is sort of like a thing I've been working on for a couple of years now, and it's a distillation of kind of all the concerns and all the sort of the theories I've had up to this point in the slide deck into a single device that tries to embody those principles. It's simple in construction, it's open in design, and it's hopefully sufficient in function to do something. It's not going to do everything, but it'll do enough for the things that people might be worried about. So within scope of the device, I consider to be things like secure text messaging, voice chat, multilingual capability is a thing I put in there to make sure we have at least enough capability to not just make it like ASCII only, but we can also handle other languages. Password management and crypto wallets would be another application space for it. I don't think you are going to run a web browser on this. You're not going to play a lot of games on it, and it's not really good for photos and videos. So it's not going to replace a mobile phone device, but it will supplement it. And the idea that right now I find that this deep irony in that we do a lot of 2FA that became a kind of a standard in terms of like authentication. But then we take the two factors and we condense them into a single device, right? So you go ahead and say, you're in your mobile phone logging into your website and it says, can you please give me the thing on your authenticator? You swipe up, your authenticator's there, you swipe back and you put your code in. Okay, so if your phone's compromised, you really only have one factor. You don't actually have two factors, right? So part of the idea here is to try and bring back that true second factor into the security equation in a form that complements the actual device that you're using to do the web browsing. So Precursor itself is by design simple in construction. Here's sort of like a montage teardown of what's on the inside of it. You can actually see there's not a whole lot of parts on the inside. There's not a lot of adhesives being used. We actually used mechanical screws to hold the thing together, which is kind of hearsay in the design world these days. But you've got to be able to take it apart to inspect it without breaking it. We use a physical keyboard because physical keyboards are just easier to inspect. There's no silicon chips. We handle the multilingual issue by having an actual overlay that you can place onto the keyboard. So you can see up here in the middle what that overlay looks like. You can imagine putting different layouts on top of it and putting it on top of a generic key switch array. And the verification of it's trivial. So we actually picked, for example, a white PCB material, so that actually it's semi-transparent. It's a little bit easier to look at than the green stuff. And you can just hold up to light and show that you have key switches and nothing else in between. And compared to a touch keyboard, the verification actually is much harder than it seems because a lot of the CapTouch controllers have proprietary firmware blobs in the inside. They certainly have a bit of memory. They can go ahead and store things. Let's see, where can we find Precursor schematics? You got that, okay. I think that's been handled. In terms of the output surface, I've picked an LCD that I think is verifiable. It's a high DPI black and white screen, 200 DPI, so it's reasonable resolution, 336 by 536 pixels, a little bit weird in terms of the aspect ratio. And most importantly, all the drive electronics are literally on the glass. So it uses TFT transistors that are imaged onto the glass. On the right-hand side is an image of what it looks like if you just take your put this under like a regular microscope. It was actually taken with the microscope sitting over here. You can see it in frame to my right. And you just sort of take your phone, the light inside your phone, you shine it through the edge of the display. There's a little bit of masking film on it, but you can get enough light through it so you can take a picture like this. And you can actually see the construction of the circuitry. People who have done a bit of circuit design will recognize sort of the general shape of this is sort of standard cell sort of libraries that have been built into the screen, and there's like an address decoder there and some other stuff going on. So you can actually you can look at it and sort of check that the circuitry is all in place. And this is different from the situation of like a color TFT LCD, because almost all color TFT LCDs are too complicated to have the circuitry built onto the glass. Instead, they rely on a full chip that's flipped onto the glass itself, and that chip will contain a frame buffer and a command interface, and like all that sort of stuff that could be used to potentially do some screen grabbing or grab a frame or something like that, or report it out through an alternate port. And so in terms of the design itself, I've got sort of I've not only have I tried to make it simple, I've actually tried to take some effort to document it, to show what everything is. So people who are not experienced in the art of circuit design or have looked a lot of PCBs, we have diagrams and documentation to sort of show you what's going on. A lot of these diagrams are published online now, and you can download them. And in particular, I went ahead and designed the PCB thinking about it in terms of attack surfaces, right? So I've actually divided the circuit itself into an untrusted U domain and a trusted T domain. So the untrusted domain is sort of where all the physical interfaces and the world interfaces go. So by definition, you have to plug in some power. That's a potential attack surface if you worry about things like glitch attacks. You have a Wi-Fi interface, which is going to have, itself will have some blobs on the inside, but whatever the whole internet, the routers you connect to, the cable modem you're using, all those things are untrusted. So I view that as an extension of that. And I bring them all together into actually an FPGA, a small UP5K that's inside the U domain, which serves as a kind of a little firewall. We don't trust that it is running the code we told it to, because it's the firewall. It's kind of attackable. It's out there. It's sort of your sort of a defensive mechanism, but it is open source. We can see everything that happens at that level at least. And then we sort of neck down all of there's this line along the middle here where we neck down all the IO into an innumerable attack surface of things that we have to worry about, things like the keyboard attack surface, sort of some things about the way the LCD is driven, the debug ports, whatnot. And then on the right-hand side, we have the trusted domain, where we go ahead and we stick our core computation, our keys, our SRAM, our audio interface, the keyboard, the LCD, all that sort of stuff is now inside the trusted domain, right? And so we can actually now reason about where the attack surface physically on this device, right? And we have some GPIOs, we have USB and power, we have JTAG, audio, keyboard, and the communication buses to the outside world. And we can go ahead and say, okay, if we want to seal them, here's what we have to do. Here's where we have to put the glue. Here's like, we can now have a conversation, I think, about sort of the potential vectors and are they adequately sealed against different threat vectors. Now, the hardest problem in doing sort of an evidence-based trust, though, is the CPU or the SoC. And this is where I think hopefully it gets a little more exciting for people who are particularly into the RISC-V end of things. The problem with silicon inspection is typically destructive and hard, right? It's difficult to both check and use a specific chip. So we can get these wonderful cross sections like IBM put here on the right-hand side, but you can tell that they actually have to slice through the chip. You're not going to use that chip anymore. You know what's inside of it, but you're not going to use that specific chip. So on the side of sort of openness and sort of open source, which is what RISC-V gets us, does it get us to the point of closing the time of use gap? It doesn't. But it does get us the ability to have experts look at the architecture and potentially find vulnerabilities. And in particular, when it comes to side channel analysis, so for example, Spectre and whatnot, the cool part is that we could actually look at the hidden machine state inside of an open source CPU and do analysis. So we're no longer in a situation where we have to just simply turn off branch prediction and we have to turn off caching, or have to turn off all the optimizations because we don't know what those things do anymore. It's theoretically possible with an open source CPU for us to go ahead and say, well, this is the branch predictor. I can go ahead and have the optimizing compiler use these optimizations inside the secure region, and we know there won't be side channel leakage because we can do some static analysis or something to get back some of that performance, even in very secure code paths. So that's one thing that openness does get you. But what OpenSilicon doesn't get you is solving the time of check to time of use problem. Even if you have a trusted fab, you still have inspections, couriers, warehouses, whatnot. So checked masks is not the same thing as trusted silicon. I don't consider the trusted fab to be in scope as a result, or necessarily even relevant. My argument is that you should just pick a tech node that meets your requirements, right? So if you already have to deal with the fact that someone can tamper with the board en route to you, all the effort you went to securing a multi-billion-dollar fab is just thrown away, right? So you might as well just say, okay, let's just use a 40 nanometer process. Yes, we can't look at it underneath the microscope, right? But at least we get some performance benefit for all the risks we're taking in terms of the supply chain footprint, right? But aside from even having to worry about sort of the fab and verifying silicon, which it's a very hard problem, and it's a problem that I do want to worry about eventually, and it's on the list of things to do. In terms of getting something into people's hands today, the FPGA actually is a pretty cool approach to solving the time of check to time of use problem. So for people who aren't familiar with FPGAs, they're field programmable gate arrays. They're basically huge arrays of logic and wires that are user configured, field configured to implement hardware and designs. And this is like just a personal side note. I was so confused when I heard field programmable gate array, because I was like, what field effect are they using to program it? Is it electrical field, magnetic field? And when they say field program, they mean like field application engineer, the guys who go into the field as opposed to in the lab to do things. That's what the field in FPGA means. It took me a long time to figure that out. So the idea is that an FPGA narrows the TOC2 gap by allowing you to compile your own system on chip. So by using a system, we're actually in Precursor using a system called Megan, which is Python based, to go ahead and describe hardware. Anyone can go ahead and compile their design from source, and that gets us back in a situation where we're transferring trust, a bit like software, right? There's some subtlety in the tool chain flow, like some flows are fully open source, some of them require vendor tools in the middle. But at the end of the day, you do get the ability to inspect the design source at least and confirm that there are no bugs and also no intentional backdoors inside of it. By also compiling your own design from source, you also get to do a bit of an ASLR type trick. So people who have a security background may have heard of this. It's called address space layout randomization. So the idea here is that if you go ahead and manage to get a buffer overflow on a device, a lot of times the attack is facilitated by the fact that there are well-known locations of all the kernel primitives. Like now that I've got stack smash on your machine, I can just call this one function and now get God mode, right, on your device. ASLR takes advantage of sort of virtual memory mapping and link time remapping to go ahead and say, nope, every single computer has a different address map. So yet another layer of difficulty for an attacker is to discover where the location of their attack primitives are, right? And so this isn't technically security, it's more security through obscurity, but it's found to be quite effective, right? This is sort of like you use ASLR. You don't say, because it's security to obscurity, we turn it off, right? People just use that in software. In the FPGA world, you can do that too, right? Basically adding a little bit of a randomness to your design, depending on the tool chain. You can go ahead and change the location, the specific location of where key primitives are. Like, where's your program counter? Well, it's not always in the same place every single time you build it. And so if you want to go ahead and put an implant on the program counter to read it out, you're basically going to have to, backdoor every single cell inside the FPGA, which creates a huge detectable footprint. And so the idea is it moves the bar from having to look for small mask level changes. So on a fixed ASIC, if I want to backdoor the program counter, I know where it is. I can route some spare cells to it. I can go ahead and put an XOR on 1 bit or something like this that may be triggerable through another exploit or something, to the issue of having to go ahead and basically change the die size of your FPGA to go ahead and backdoor every single primitive. Just a simple recompilation of the random parameter will do the trick on the 7 series for Xilinx, and other series you just recompile it because they use random seeds. In terms of sort of addressing the problem with closed source tool chains, at least in the 7 series, there's an effort to make a bitstream decompiler for it. And this has gotten quite far now. And the idea is that you can go ahead, even though we don't necessarily know exactly what the compiler is doing, you can look at the compiler output to inspect that it's not doing something different or something unusual or something strange that you haven't seen before. And you can also ask questions about what these different bits do in the bitstream, and we can edit them and lock down bits that we don't think that shouldn't be there, right? So just a quick summary of what sort of FPGA versus custom silicon looks like. If we were to go ahead and do custom silicon and run it at, say, 40 nanometer, we could get a true single clip chip device that runs at 500 plus megahertz speeds and consumes a minuscule amount of power. The downside of silicon is that it's hard to verify. Open source doesn't actually help much with the verification problem, and the IP blocks itself, so like even the SRAM blocks are oftentimes closed source blocks from a vendor, and verifying those is a really hard problem. On the other hand, FPGAs offer immediate mitigation for things like inspectability of the source, the bit streams. We can randomize the logic mapping. We can do per device unique pin mapping, which allows us to do board level mitigation of implants. The problem with FPGAs is that they're just barely good enough to do anything with. You have to use external RAM, maybe encrypt that, which is a big performance hit. It only runs around 100 megahertz speed in practice, and it's going to consume about 5 to 10x the power of sort of the equivalent piece of silicon. All that being said, Precursor does use an FPGA because I think that is the solution we can have today. And it goes ahead and it moves the bit, sort of the point of check closer to the end user. It sort of moves that bar a bit further. Ideally, someday we have some sort of one-click tool that can allow us to verify a bit stream. That doesn't exist today, but that really does mean the point of check is now at the point of use for the design itself. So a bit more about that FPGA, the Precursor FPGA socket itself. This here is a block diagram of what goes into the SoC, and I'm going to go through every single one of these in order. You don't have to sort of stare at this too much right now. This sort of just give me an idea of where we're going with the talk. Before I get into it, this is what that design looks like mapped to a piece of silicon. So this is an amoeba plot that came out of the design tool that we use, of Vivado. And you can see the major blocks take about same amount of space each. So the AES block, the SHA-512 block, SHA-2, and the Engine 25519, which is a Curve 25519 accelerator, all take about the same amount of space as a Vexris 5 core. There's a tiny little key ROM on the inside, and basically everything else on this diagram here is a rounding error, right? Beyond sort of like those huge cores, you can't even really point to them in the amoeba plot. They're so small. So talking about the core complex. So a core is a single core RISC-V CPU. We use the RISC-V32 iMac sort of subset of instructions with an MMU. The MMU itself is a little bit weird to have in a very small embedded device, but we figured since people have spent so much effort figuring out how to secure systems with MMUs, it'd be a shame to not use that technology, even though we don't need it for huge amounts of virtual memory. We can use it for process isolation. We can use it for sort of catching stack smashes and whatnot, right? So that's we use an MMU in this, and we actually write an OS around that. The specific implementation of RISC-V we use is the Vexris V implementation. We have a small amount of on-chip RAM and ROM for some housekeeping functions. Those are all open source. You can see what's inside a ROM. Some housekeeping blocks, and we also use LIDEX for integration. Housekeeping blocks are stuff like, controlling reboot of the CPU, reset vectors, timers, clock generation, and we also burn in like the latest Git info into the actual chip itself. So once you blow the bitstream on, you can see what Git tag was used to build the particular revision of the chip that you're looking at. A little more on the Vexris V CPU. It's fully open source. You can go to the URL given this presentation here to look at it. It's written in Spinal HDL/Scala, which itself is sort of like a cousin of Java. I have sort of a weird relationship with this language. I'm still trying to figure it out. Definitely not the most intuitive thing for me to sort of read, but here's an example on the right-hand side of what it looks like. The cool part is that, you can sort of just look at it and be like, okay, are there any opcodes I don't expect to see inside the source code, right? It's not terribly inscrutable at that level. And you can go ahead and likewise modify it to add any opcodes you need to add for functions that you are looking to do. There's mechanisms inside the RISC-V spec to accommodate that. One of my a recent thing that happened, which is I think it was really neat, is that on a closed source CPU, if you found a hardware exploit, they would give it a name like, oh, zombie load or Spectre or whatever it is. Like, oh, we found a way to go ahead and leak some information from the secure domain, right? Recently, the maintainer of the VexRISC-V found a small privilege crossing issue inside the CSR plugin and reported it. He was like, hey, by the way, a certain sequence of accesses can go ahead and cause a privilege issue, right? The guy just sent me an email and said, here's a patch, and you just commit it and we're done, right? If I had fabbed out silicon behind this and put like, even 100,000 units out there and someone found this, it would be like, I don't know, it'd have its own website and a logo or something like this, right? In the open source world, it's just a commit and a patch, and you rebuild it and you put in your FPGA, which is something that like I super love about this level of design, this level of transparency, and the sort of agileness of FPGAs. For people who haven't heard of LIDEX, and I don't, normally if I were in a meetup, I would ask to see who has heard about it here, but now I can't do that. So I'm just going to talk about it and guess that you haven't heard about it yet, or some people haven't. It's actually a really powerful SoC integration framework. You can go ahead and check it out at the URLs I've given. It's written in Python. It doesn't mean that your code actually executes Python. Python is used to describe a sequence of Verilog that's generated at the end of the day. So it's just it's a fancy way to go ahead and proceduralize the generation of Verilog. It supports multiple CPU types, so not just RISC-V, but you can do multi-core RISC-Vs. You can see the Rocket is supported. Pico RV32 also supports sort of quirkier architectures like the Aura1K, LM32, has PowerPC, I think through the microwatt, a bunch of different things, right? And the cool part is that if you want to go ahead and change which CPU you're using, it's literally, if you look on the right-hand side, there's a CPU parameters line here. And right now it's just a coded string VexRISC-V. You just sort of change the code string out to the core you want, and it just generates that core for you. It's like really, it's like shockingly simple to go ahead and swap that. Of course, the software layer is a big issue, is a different issue. You have to write the software, right? If you don't like the core, you can go ahead and just change it out with a single string. It also does all the system on the SoC integration for you, so you can go ahead and merge Xe, Wishbone, and CSR together on a single chip, mix and match. It creates different memory spaces, cacheability, non-cacheability, all that sort of stuff comes together. Has support for multiple masters on the buses, debug modes. You can throw a sort of a logic analyzer into the SoC itself to go ahead and probe different points and then read them back out later on. So it's actually a really powerful integration framework, and I'm happy to field questions about it later on if people haven't used it. Beyond the core complex, I have a debug complex that's built in. So our methodology is to debugging over USB. So we don't have JTAG because JTAG requires proprietary adapters and whatnot. We did start with that, but we've now moved to a USB full speed core. So you just plug it in, it shows up as a device, and we have a tool called Wishbone tool that goes ahead and you can just peek and poke different registers inside of your SoC over USB. And we've put a lot of effort to go ahead and try to. Oh, thanks for the poll. That's cool. We've put a lot of effort in to go ahead and try to improve the performance of the USB core. So we've got burst support in now. We can transfer a couple of megabytes per second, or I think about a megabyte per second. Over the USB bus now, so we can get some good performance on it. And we also expose CSR-based registers, so we can do things like GDB over USB and whatnot. We have this also weird trick of where we just create a FIFO that has CSR registers exposed for both the in and out, and we use that as a message passing device between the debug realm and software. So, for example, when I'm testing the TRNG, I need to synchronize as to when the TRNG buffers are filled in memory. I just go ahead and I throw a word into a FIFO, and I have the debug bus sort of watch it. And when that word, the keyword sync word appears, I know that the TRNG is filled in memory. I can read it out via a USB and then throw it into Die Harder and check that like all the random numbers are okay. Obviously, this sorts of stuff needs to be compiled out for production. If you leave this in, anyone can plug your precursor device into USB and then read all the secrets. Let's see. After the debug complex, we have a bunch of CSR-based I/O. So these are kind of simple I/O bus type housekeeping things. I2C, events, keyboard, JTAG, ADC, UART, GPIO, sort of the COM bus to the outside world is currently implemented using CSRs. Not a lot to talk about here, but if people have questions, happy to go into them. I've also provisioned a bunch of memory map I/O. So memory map I/O has a direct wishbone bus connection. These offer a slightly higher performance, and it's a little bit easier to write software for them by putting them in the memory base. I think someone asked a question here. Yes, the USB is also open source. The USB core we're using is Valenti USB. It's actually, if you go to the GitHub repo, btrustedIO / btrustedsock, under /deps, you'll see the link to Valenti USB, and we use that for the full speed core, so it's fully open. There's no, we're not using vendor core for that. Okay, so on the memory mapped I/O, we have external RAM that is done through this, audio, a flash controller up to 120 megabytes through an interface we call OPI. It's actually sort of weird to call it SPI now because it's actually an 8-bit wide parallel bus. So they call it SPI OPI. Increasingly misnamed trilogies that have 12 sort of books in it. We're now at 8-bit wide serial buses. And it's double data rate, runs 100 megahertz. So it actually pushes a decent bandwidth. And actually, you can almost do XIP out of it without any delay on a 100 megahertz CPU. And it does prefetching as well. So if you're doing just straight line code, actually there's no delay at all. The prefetcher will help you keep up pretty much. And an LCD controller with a frame buffer as well to offload some of that from the CPU. We have a cryptography complex that we've put into this. So we sort of decided to accelerate some common protocols. AES and SHA were opportunistic. We're using the actual Google OpenTitan system Verilog cores that they've made available very kindly through their site. And SHA-512 actually isn't part of the system Verilog that Google shares. So, but it's actually, they wrote their SHA-2 course, so it's easily extensible to it. So we have both of them in there right now, even though we plan to move to SHA-512 for everything. I left the SHA-2 in for now. It's just eating gates, but we have space for it. And we have a Curve 25519 accelerator. I'll talk about that a little bit more in the next slide. We have a key ROM that we use for key storage. And the reason why this is called out separately is I actually do a trick where I hard locate the LUTs inside the FPGA, which puts them in a specific spot in the bit stream. And I've written a tool that allows you to use a TRNG to generate keys and then actually patch them back into the bit stream on the actual device itself. So that way you can self-provision and poke those things into the bit stream without having to use any third-party tools or even recompile the FPGA itself. You just edit the bit stream directly. We have a hardware TRNG that's ring oscillator based inside the FPGA itself. We also have an external TRNG, so we use a dual TRNG architecture to try and get around some of the observability versus security issues behind TRNGs. Happy to talk about that more. And I also like to always leave in any diagram of security where the debug buses are. There's a facility inside the 7 series called the ICAP. It's an introspection port that allows you to look at all of everything on the inside. If you don't tie it down, you lose. So we just put an explicit tie down out of it, so no other blocks accidentally claim it without our knowing. We have a Curve 25519 accelerator that I built. It's a 256-bit wide modular arithmetic CPU. So it's a really simple non-bypass pipeline. Bypassing would be incredibly expensive in something this wide. But it can do a field multiply with normalization in about 52 cycles at 100 megahertz clock rate. So normalization is you're not doing a straight binary multiply. You'll get things that are bigger than the field itself. So we actually have to figure out if we've like overflowed the field and do carry propagates and stuff. So that all happens in those 52 cycles, not just a multiply. It's about a 40x speed up on a Montgomery scalar multiplication, which is a core operation in Diffie-Hellman key exchange. So we go from about 100 megahertz, 100 milliseconds benchmark speed on the RISC-V that we have right now to about 2.3 milliseconds in hardware. And the reason why we spend so much gates on this is that if you're going to do a secure messaging protocol like Signal, they use the double ratchet protocol, and they're just doing an obnoxious amount of Diffie-Hellman exchanges, like 2 or 3 per message or something like that if you're doing it right. And if you're talking about 100 millisecond delay on the UI every single time you're sending a message, that gets obnoxious at some point in time. So we felt it was very important to do a dedicated hardware engine. Another approach, completely valid, and someone else can do this quite easily, is just to create a second RISC-V core. It turns out that this engine is bigger than a RISC-V core. So if you wanted something in the middle that wasn't so highly accelerated, you could just go multi-core, write an accelerator that runs in software, and just throw it to that. It's another approach you could take, right? It's open source. Go ahead. Let's see, a bit more on the dual TRNG architecture. So the reason why we have two, one on chip and one off chip, is that an off chip TRNG is easy to verify, right? So you can go ahead and just put an oscilloscope on our Avalanche generator and see sort of like that it's operating correctly. It's not saturated. It looks randomish, right? We understand the physical principles behind it. But it's relatively easy to tamper with if you actually can get physical access to the device, or you can irradiate you with high amounts of microwave or something like this. You can go ahead and rail the TRNG, right? It's easier to tamper with. And on on-chip TRNG, a ring oscillator, it's harder to do that, right? But it's also harder to verify. It's harder for us to just put an oscilloscope on that TRNG and confirm it's running. Even if you could pipe its output to a pin, you can still put a bypass on the inside to something else that's more deterministic, right? So you can't actually see what's going on. So our recommended approach is to have both of these and XOR them together, right? Entropy is great. You just keep on, if you XOR a fixed pattern with the entropy, you just get entropy, right, at the end of the day. So you sort of like have your cake and eat it too scenario. The main trade-off is power and area, and both of them are within acceptable bounds for this. So that's sort of a really whistle-stop overview where we are on Precursor today. Just as a reminder, we try to keep it simple. We built a whole system, so we're not talking about just chips, but we want to extend the security boundary all the way to your eyes and your fingertips. And we also want to empower end users to sort of self-seal and verify their hardware. And the whole idea is to move that time of check, time of use gap closer to the point of use. So even if you yourself are not an expert in one of the areas that is necessary to verify your device, probably you know someone, or you know someone who knows someone that you trust that has your same values, that you can get an opinion on it, right? It's open enough that we can do that. So I don't expect that everyone literally takes their device and pulls it apart and knows enough to check everything. But the idea is to put enough information out there and make it simple enough that an expert could conceivably do it within a humanly reasonable amount of time. The problem is that even if I gave someone the Linux kernel source and it says, please analyze all of this and tell me that there are no exploits, by the time they finish analyzing it, their kernel, Linux is in like 3 major revisions later on with a bunch of security patches that have to be re-revised. So it's like it's an intractable problem to sort of analyze something that complex and guarantee that has no exploits. Current status is that we're crowdfunding Precursor now. So if you found it interesting, this is where I do the pitch. Go to precursor.dev, have a look at our campaign, and please consider backing the project. Even just going to the Buy Us a Beer link helps to go ahead and get us to the point where we can actually pay for the tooling and actually also help pay for ongoing development support for it over the coming years. I'm not the only person who's working on this. We've actually got a whole bunch of people who are contributing, but notably the software side is handled by Sean Sobbs-Cross. He's writing like a full OS. It's a crazy hard problem. He's spent the last year working on it. It's now booting. It's you know, we've got inter-process communication. It's super cool. It's written in Rust, and I'll let him talk about that someday in a talk. You should definitely check it out. And we're now just starting to think about the UX and application layer. I have to give a shout out to NLNet for giving us funding to get us this far. So we actually were able to get really, really far on a product development without having to do crowdfunding, thanks to the money that came from the NLNet Foundation and NGA Zero. And here's a link to the website and my socials. And I'd really like to open up to sort of questions to people who are here, and thank everyone for coming and spending the time to listen to me at the talk.
All right, looks like we've got a current one from Michael. Do you see a current business use for Precursor?
Do I see a current business use for Precursor? Yeah, definitely. I think that there are applications in the business world. So a big problem, and a big and growing problem, is like spear phishing of you know, comptrollers and executives lately. So it's a documented problem. Like I think it was even Air Electronics. The CFO got duped into transferring like $4 million into a bank account because they got an email saying like, hey, like we've got a deal going, we need $4 million in Hong Kong. Like, and she just, you know, sends it over. You can't verify the people because, like, you know, the whole thing was compromised. Spear phishing is a human problem fundamentally, but having a second factor can help. So if you're going to have, you know, like a CFO or something like that, a big organization, and you want to, you know, authorize huge transactions like this, you could imagine them just keeping on hand, you know, a device like this and just having a quick chat, like, hey, just checking on a secondary method. Did you authorize this? Right at the end of the day. Right. So that could be conceivably like a solid business proposition. Obviously, if you're a bank or doing some kind of currency trading, this as a second factor would be interesting. It's a bit expensive for everyday users, and that's just by the nature of FPGAs. But there are users who have that level of exposure and would possibly find it worthwhile.
All right. And as the name implies, Precursor is kind of only the start of where this can go. So as hardware gets cheaper and resources get smaller, you can pack more in for less as this line of products continues.
Yeah, that's the idea. The whole idea, actually. So a little bit more in the history of this. People who have been following me may have noticed I did a project. It was originally called Be Trusted, right? And the idea behind Be Trusted is that I had a much more ambitious vision for Be Trusted, which was I wanted a complete end-to-end, user-friendly, secure communications solution. So basically, safe defaults. You don't have to install any software. You just pick it up and you can trust it. It's a thing I could hand to my journalist friend who knows nothing about technology. They're going to go, you know, and report in a very dangerous region. And I say, this will keep you safe. Bring 5 of them with you, hand them to your contacts, and your contacts will be safe too, right? But you know, that's the level we want to get to for this type of thing. The problem is that software is really hard. You think hardware is hard, software is like, yeah, you know, securing software and making sure you don't have any exploits and whatnot is a very difficult problem, and it's going to take years to get to that level of software integrity. So being realistic about it, I was like, okay, we're not going to just hold off the whole project until the software is ready. We have a precursor. We have a hardware platform that, you know, software teams who have different requirements than me, who are more clever than me, can go ahead and start doing things with. Why not, right? We should just make it available. And to avoid confusion, I don't want to fight with the community over like who owns the branding of Be Trusted and what does it mean? Because you know, if someone goes ahead and makes a secure communications device, that's not meeting my standard, but it's good enough. I don't want to be like, you can't call it Be Trusted because it's going to confuse the journalists, right? Just pick your own brand, run it on Precursor, and have a day, right? I want, and so the split of the hardware into its own brand that is agnostic to the application is a nod to the idea that the community should feel empowered to own it and fork it and develop with it. And I don't want to be at odds with the community in terms of my overall vision for what I want to take Be Trusted.
Makes sense. So Jan has a question about, Are you doing anything to protect or encrypt off-chip RAM or flash access? Do you need oblivious RAM, etc.?
Yeah, I thought about that problem. It's possible to encrypt the RAM, but it does incur a pretty big performance penalty. And in light of the existing attack vectors that if you have physical possession of the device, particularly, unfortunately, the level of security you get from a Spartan 7 isn't perfect in terms of physical security. There are exploits on the Spartan 7. If you can physically get the device and you have a good milling machine and you have good probes, you can pull secrets out. Unfortunately, that's just the nature of the business. Given that, I felt like the performance loss of encrypted memory was probably too great. And so sort of my solution to that is to be like, well, put some epoxy on it. That's what we do anyways with chips, right? Like, when we get those little black blobs, we think of them as chips. Actually, sometimes they're 2 chips and 3 chips, 4 chips on the inside, right? And we say they're a chip, right? And we call it good enough because the epoxy is hard to remove. So I sort of fall back to the argument of epoxy is going to be good enough. And if you have an adversary who is going to take the effort and put it into like a special milling machine or something like that to remove to access your device, then we have to start having chips and doing a different level of physical security.
Makes sense.
Yeah.
So I wanted to know, are you accepting community input for this or contributions? And if so, are there any specific areas? You had mentioned software maybe being one of those. Are there areas where you really want community support, or are there areas where you're kind of, look, hands off for now, we want to finish this up and hand you something that we have built?
It's a good question. We're definitely looking for community support. I mean, like, we are, the part of the reason we decided to do crowdfunding is literally to try to get community. The big thing we actually really need the most out of the crowdfunding is, in addition to just getting over the money to pay for tooling and stuff, is community building, right? We really need you. We need everybody's help to make something this complex. Like, normally SOCs are done by teams of like 40 people over 2 years with multi-million-dollar budgets. This thing's built in this lab you see right behind me, mostly by me, right? The hardware. It's like, I don't have a lot of resources, and I'm just one person. So I'm very realistic about how hard this problem is. The software problem is even harder. Sean's been like really busting his back to get the software to the point where it's running, and he's done a huge job on that. On the kernel, but then we have the application level stuff. We have the UI stuff. We have, file systems to worry about. We have protocols to deal with. We have, like, there's a huge amount of stuff. So really, at the software level, that's going to be a big open question. The good news is Sean has actually, and he's putting out a campaign update on this soon. He's got a methodology where he uses Renode to simulate the whole precursor device. Most of it, that you need at least to boot the OS and whatnot. And so people can start software dev before they get their devices, right? By downloading the emulator and running code, which is super cool. And in terms of the hardware side of things, I'm trying to button it up and get it ready for shipping on the campaign. Like, basically, we're at a PVT rev, so I consider it pretty stable. Definitely on the SOC side of things, improvements and help on improving the SOC code base is welcome. You can take a look at it. I think we're getting pretty close to shippable, but there's stuff like, man, it'd be nice if we could get a little more performance on the USB core. It'd be nice to have a little more, rub the rough edges off of the COM bus. My current focus is trying to get the embedded controller a little more stable and whatnot. So there's a lot of details to deal with, and so we'll definitely accept community help where we can get it.
All right. So along those lines, Dylan wants to know, would any of the existing FPGA platforms make sense? And I'm assuming as a precursor, as he refers to it, to get some software running that will be compatible with the product once you get it in your hands. Is anything actually suitable for that?
Yeah, I'm reading the question. As a precursor development, would any of the existing? Okay, so basically, is there a dev platform they can use to go ahead and get started? Yeah, so I think that I think so. If you're trying to do software development, probably the best way to do it is to go to Betrusted IO /XOUS-core, and the README there actually will tell you how to install Renode and get the emulation layer going. Right. So the emulator is actually going to be the most accessible way to start thinking about the problem of getting software running on it. If you want to actually dev on, like, for example, our gateware IP blocks at the FPGA level, unfortunately, things like the display and the keyboard, they don't exist on the other platforms. So if you want to work on it, again, the most effective way is to look at our simulation benches. Actually, we simulate all of our gateware IP before we put on the FPGA. We don't just sort of like blow it on and hope that it works, because that's just too slow. So I have a set of pretty good simulation benches. If you go to betrusted-io/gateware, and that's on GitHub. All these URLs are giving you in GitHub. The gateware directory has a /sim directory, and in there has different blocks that we've developed inside. So you can actually see on Curve 25519, we actually simulate a full Montgomery scalar multiply in XSim as part of the process. So we have really detailed simulations of all the blocks are running. So you can go ahead and dev on that. We actually have, like, if someone really wants to cut their teeth on crypto stuff on the Curve 25519 engine, we have this microcoded assembly that we use, and we're going through the Curve 25519-Dalek crate, Rust crate. So if you know Rust, and we're trying to accelerate the full operation. We have the core scalar multiply accelerated, but we don't have the there's a final sort of stage where an inversion has to happen, and it's just a matter of translating a couple Rust functions into this macro language that we have in assembly. If you're interested in doing that, you can ping me. I can point you to all the instructions to do it. But basically, you have to know a little Rust, a little crypto, be okay with assembly coding to kind of make that happen. So it's that's on the to-do list, but I just haven't managed to get to tying down that loose end.
Bit of an involved process, right?
Yeah.
And let's see. And Jan would like to know: are you considering any custom instructions to the VEX RISC-V core, and if so, for what purpose?
Yeah, we haven't had a need to customize instructions. We have had the need to patch some bugs or some oversights, which is cool that we're able to do that. So, like in the implementation of the page register, I forget what the name of the register is, but there's a bit field called the ASID that Linux doesn't use, and so they didn't implement it, but we actually used the ASID in Zeus, and so we were able to actually just go in and like implement it, which is great. It would be a nightmare if we couldn't get that field back. That's in the spec. So that's some stuff that we've done. In terms of like actual specific instructions, the problem with building really specific instruction add-ons is it makes other people's development process a lot harder, and have to get other people up to speed on the compiler. We'd have to get our own tooling going and that sort of stuff. So we've generally avoided that. And so, as I mentioned even before with that Curve 25519 engine, trying to bring someone up to speed on how to write the assembly code for that engine, the microcode for it, is a process in and of itself. Someone has to be willing to spend, it's probably going to take an afternoon at least, to just become familiarized with the state of the code base, as opposed to using RISC-V. It's like, oh yeah, just download GCC for it, or Clang, or whatever it is, and you've got a binary that runs, right? So that's a great situation to be in. I want to stay there.
Sounds right. All right, it looks like that's the end of our questions. Going once, going twice. Anybody have anything more they'd like to ask? Looks like a few people have finished up. Okay, Andrew, thank you so much for being the speaker for this talk. It's extremely awesome that you were able to make the time. Everybody, please go check out precursor.dev. Check out there's the hardware there. I wanted to say beautiful design, by the way. It's it just looks like it would be something really fun to hold. Besides digging into the guts of it, it looks like something I'd like to.
Yeah,
What the heck?
I wanted to make it a thing that you could actually carry around in your pocket and like actually like just use on a daily basis. That was really important, one of the important aspects of it. So there's actually a whole bunch of cool tricks that we'll talk about more in the campaign. But like, sorry, I'm gonna co-opt a little more of your time.
Not at all.
The like the bezel itself actually is not it's a PCB. It's actually FR4, and that little logo there is actually a 2.4 gigahertz antenna. So
Nice.
we use the PCB material as a dielectric, as a structural material, and as an RF medium. And because it's a PCB, you could, if you could convince a PCB shop to do step milling for you, you could make your own
Right.
bezel for it.
That's beautiful.
And a bunch of stuff like that. So like, I tried to make it, pretty, sort of pocket friendly.
Right.
And we've been deliberating on some like, what the omakase version is going to look like in the campaign. So we've got a version here that's made out of, this is naval brass.
Wow.
So it's really beautiful. It's really durable. And it can handle salt water, and I mean, not that the device is waterproof, but you can put it in your pocket.
Don't drop it in the water, people.
Yeah, don't drop it in the water, but the salt from your body, right?
Right,
The sweat and whatnot from your pocket will give it a nice sort of color to over time. It'll age. Like, it's actually, I like the material because it's one of those things where over time it looks better as opposed to worse. Which is why I'm considering that for the omakase version. So like we're working through some of these details right now, but I just figured since we're at the meetup and people made the effort to come, I just show them sort of things that we haven't talked about
That's awesome.
publicly.
Is there any possibility of extending? It looked like all the omakase level crowdfunding was taken up, or is there a possibility of extending those slots if people are interested?
I think omakase is available, just not the early birds are done with. So
okay.
it was unit limited, time limited thing just to sort of get the campaign moving.
Gotcha.
But you can order. We'll take orders on the omakase all the way until the campaign closes. But because of the expense of working with these materials, like actually this stuff is beautiful, but it's hella expensive. It's actually pretty expensive even prototype with it compared to the aluminum cases. We won't be offering. We don't want to be in the business of stocking slugs of bronze or brass. In a distributor. It's not easy. So it really is just a campaign only thing.
All right. Well, once again, thank you so much. Again, everybody, precursor.dev, check it out. Please fund this awesome project, even if it's just buy them a cup of coffee, a couple of coffees or more. And I'm eagerly awaiting being able to get on there myself. So thank you again, Andrew, so much. And we look forward to hearing a lot more from this.
Okay. Thanks, guys. Thanks, everyone, for coming and dropping in. And I wish, hopefully Sunday when the pandemic's over, I can meet you face to face. And it would have been cool to sort of pass these things around and have you guys look at it and feel it. And like, it's so hard because like, I'm a hardware guy. Things like material finish and weight of the product really matter to me, like these details, and virtually it's so hard to even communicate like all these things I'm going through. But someday we'll be
hopefully
able to meet a person.
That will be in another book. I'd love to see it.
Well, I'm writing a whole bunch of campaign updates, so stay tuned there, and we'll be talking about like the case design process, the PCB process, everything. Like I really want to sort of put it all out there, how it was built and all that sort of stuff. So you'll get more, and some of these posts are kind of unintentionally turning into book chapters.
I think they're very informative for especially the newer engineers that are just trying to get their feet wet in this. Your experience and the way you are depicting it and sharing that for other people, I think, is really welcome. So cool. Thank you on behalf of everybody else who really enjoys reading those.
Well, thanks everyone for stopping in and listening. That's makes it worthwhile. So
right on. All right, take care.
Yep. Thanks, guys.
Thanks, everybody, and look forward to new meetings. Hopefully an announcement in about 3 weeks, but possibly sooner for our next session. And I'll try and get this on more regular basis. So thank you, everybody. Stay safe, take care, and look forward to the next one.
Yeah. See you. Bye.
All right.